Hello, everyone, and welcome to Psych 4100 Cognitive Psychology. This is going to be our first lecture of the semester on Chapter 1. What we're going to talk about in this chapter is just a basic introduction to cognitive psychology. What is cognitive psychology? A little bit about the history of cognitive psychology, how it came to be, sort of its foundations. And then at the end, we'll get into a little bit about some of the types of tools that we use and measurements that we take in order to study cognitive psychology as well as study the brain. So some just overarching questions that we're going to sort of intersect with and maybe touch on throughout this chapter are things like, how is cognitive psychology relevant to everyday experience? Maybe we can sort of answer that question after learning a little bit about cognitive psychology. What are the practical applications of cognitive psychology? Why does this stuff matter? Maybe the biggest question sort of historically over the last maybe 50 years, 60 years in cognitive psychology is, how is it possible to study the inner workings of the mind, something that we can't touch and feel, right? We can only sort of approximate or make assumptions about. And in fact, we'll see that very issue sort of defined much of the creation of cognitive psychology. And lastly, what was the cognitive revolution, this sort of paradigm shift moment or moments that led to the instantiation of what we now call cognitive psychology. So first, what are some of the things involved in cognitive psychology? It's a relatively focused, but then again, relatively broad field, right? So cognition is basically what your brain does. Cognitive psychology doesn't necessarily study the brain itself. That's the domain really of neuroscience. But cognitive psychology studies what the brain does, the activities of the brain. And we often call this the mind. You'll hear that term thrown around for sort of the thing, the best sort of single item to call what cognitive psychology is the study of the mind. But what that involves are things all along this spectrum, from simple perception of the environment. So if we think about the eyes, literally photons, light, enter your eye, right? Hit the back of your eye and what's called your retina, where your brain starts to interpret that light and create this beautiful picture that you see of the world out in front of you. So we call that perception, just this intake of sensory information from the world. We then have to pay attention to that information. We have to try and remember that information. We have to categorize that information. We have to maybe think about that information. We can visualize it, right? You can think about things that are not right in front of you, right? If I ask you all right now to imagine an elephant wearing a trench coat, you could do it, even though you've probably never seen an elephant wearing a trench coat. And this aspect of cognition, visualization, is probably really important for things like problem solving, which is down here as well, right? We can project into the future or project hypothetical situations by visualizing them. Cognition is tied intricately to language, which is how we communicate all of these things that the mind does with other people. And then, of course, decision-making, problem-solving, reasoning, these sort of what we might call higher order faculties that are involved in decision-making. So if we had to define cognitive psychology, as I said before, it's concerned with the scientific study of the mind. So we refer to these as like mental processes, or basically what the mind creates, what the brain creates. Now, I said before that cognitive psychology doesn't necessarily study the brain itself. That's neuroscience. However, there is a sort of in-between field, a combo of cognition and neuroscience called cognitive neuroscience. And that's really just the bridge between cognition and neuroscience. So a cognitive psychologist might study memory and how and why people remember particular things and maybe forget other particular things. A neuroscientist might study how the buildup of amyloid plaques in the central nervous system leads to Alzheimer's disease. Right? Something very sort of almost biological about the brain. But then a cognitive neuroscientist might study how Alzheimer's and those buildup of amyloid plaques in the brain impacts people's ability to remember certain types of information. So we can have these two distinct fields of cognition and neuroscience, and then we can also bridge that gap with the field of cognitive neuroscience. So if we think about what the mind does, it's all those things we talked about, right? The mind helps us create and recall memories. It helps us solve problems and consider abstract or hypothetical situations or possibilities. It helps us survive, right? Without the mind as the sort of interface between your brain and the world around you, you would not be able to survive. And there's a couple different theories about sort of the way we should consider the mind. One of my favorite really is as an operating system. So just like your computer has an operating system that allows you to access the functions of your computer, there's obviously a lot going on behind the curtain, so to speak, of that operating system. So when you click on a Word document to pull it up and edit, you just see this pretty little picture of a Word document on your desktop. You click it and boom, you have the ability to function or do functions on that Word document. You didn't actually go into the brain, so to speak, of the computer and type the code that allows you to access the Word document, right? Someone has already done that, and then they've provided you with this convenient operating system that allows you to access that function. So I like to think about the mind as the operating system of your brain that allows you to access the survival and functional mechanisms that you need that are sort of going on behind the scenes in your brain. The mind is this sort of symbolic place of creativity and intelligence, things that cognitive psychologists study, but are very sort of amorphous, right? Memory or attention or perception are pretty concrete in a sense, whereas something like creativity is again more amorphous. It's difficult to study, but it is the domain of cognitive psychology. And lastly, something really important the mind does is it creates representations of the world. And when we say a representation, the easiest analogy is language. So when you think about the word horse, Horse, there are a couple levels of representation there. If you were to literally write out the word horse, right, write the physical letters on a page, those physical letters are just squiggles and lines and hoops and swoops, right? They don't have to mean anything. If you took those same movements and you jumbled them up, they would lose their meaning. But we as a society, or as in English speakers, we have all agreed that that particular combination of lines and hoops and swoops and circles represent the idea of a horse. Right? They are not a horse, but they represent the idea of a horse so that we can then communicate about horses. The same thing goes for spoken language. So when I say the word horse, right, it's made up of a bunch of distinct sounds, h, or s, which in and of themselves don't have any inherent meaning, right? If I said, that doesn't mean anything to you. But when I combine it with the rest of the noises that make up horse, we, again, as a society, meaning English speakers, we agree that that combination of sounds, h or s, represents the idea of a horse so that we can communicate about it. And so that's a really important function of your mind. It doesn't have to use language for representation, but language is the best, sort of easiest analogy to understand representation. Okay, so let's go all the way back to 1868. and look at what is probably the first experimental study of cognitive psychology. The field doesn't exist yet in 1868, but this scientist named Donders was trying to understand what a decision is or how long it takes someone to make a decision. And so he did some very basic experiments involving reaction time. Reaction time is the measurement between the onset of a stimulus and then your reaction to that stimulus, right? How quickly you react to the onset of a stimulus. So in a simple reaction time task, which is one of the things that Donders did, participants simply push a button as quickly as possible after a light bulb comes on, right? So this is 1868, so no computers here, but maybe a light bulb comes on in the room and the participant has to press a button as quickly as possible, and Donders is recording how quickly they press that button. The next task, which is a little more complicated, is that Donders presents the participant with two lights, one light on their right-hand side and one light on their left-hand side. And one of these lights will turn on, either the left light or the right light. And if the left light turns on, the participant must press the left button. If the right light turns on, the participant must press the right button. So they have to perceive the stimulus of the light turning on, but now what we've added is a decision that must be made. Light comes on, your brain, your mind has to go, is that the left light or the right light? Ooh, that's the left light. Okay, press the left button and send that command down to your hand. So it's very similar to the simple reaction time task. It's the same function, right? Light comes on, press button. Light comes on, press button. But what we've added is the element of choice. So what Donders said is that the difference in time between a simple reaction time task and a choice reaction time task, the difference in time is how long it takes your brain to make a decision, right? So if it takes 100 milliseconds to do the simple reaction time task, but it takes 200 milliseconds to do the choice reaction time task, then reacting takes 100 milliseconds and making a choice takes 100 milliseconds. So we've learned something about the mind, right? The function of the brain. So in a modern setting, this is more what Donders' study would look like. On the left-hand side, we have your basic reaction time task. Light comes on, press button. On the right-hand side, we have the choice reaction time. You have the left light or the right light. And in this case, instead of pressing buttons, right, the participant has to press maybe a certain key, the A versus the L key, or the K versus the J key. So we have this sequence of stimulus, mental response, which is really what Donders is interested in, right? What does your mind have to do to produce a behavioral response? Presumably, the mental response in a simple reaction time task, where the light flashes, I perceive the light, and then I press a button. The mental response here is more simple because there's no choice that needs to be made. Versus here on the right, the choice reaction time, where the light flashes, I have to perceive that it's, in fact, the left light, and then decide to press the left button. This mental operation is more complicated. There's an extra step. And so we can measure this extra step using reaction time. But notice, and here we go back to one of our fundamental questions about cognitive psychology, I can't directly measure the mental response yet. It's 1868, right? We have no brain imaging. We can't directly measure anything that's going on inside of the brain in real time while someone is alive. So all that we're left with is a behavioral response, a button press. And so this is going to be one of the problems of cognitive psychology, is that at the end of the day, we're presenting a stimulus up here, the light, and then we're measuring a behavioral response, and we're making assumptions about what's going on in the mind. We have to make assumptions about the mental response because we can't directly see it, touch it, feel it, or measure it yet. So what Donder found is that consistently the choice reaction time took 1/10 of a second longer than the simple reaction time. That comes out to 100 milliseconds. So we're, again, inferring mental responses or decision making from a participant's behavior. But what Donder has shown is that the mind is doing something because it takes extra time to make a decision, right? If the mind was not involved in this, if the mind didn't matter, then the simple reaction time and the choice reaction time would be equal. They would both be, whatever, 100 milliseconds or 150 milliseconds. But that's not what he found. He found that having to make a choice, left button versus right button, causes a delay in reaction time. And so he then makes the, good assumption that that delay is evidence of the mind. It's evidence of this, what I'm going to call, me personally, an operating system that gives you access to and directs sort of the energy of the response. So that was 1868. Donders maybe didn't really consider what he was doing to be psychology. Psychology really grew, of course, out of philosophy. But in 1879, we have the foundation of the very first explicit scientific psychology lab at the University of Leipzig, Germany, by Wilhelm Wundt. Wundt created or founded what is now known as structuralism. It's not exactly the way that we would sort of prefer to do cognitive psychology, and it's certainly not the way we do cognitive psychology now. But Wundt was the first person to sort of explicitly say, I want to move psychology as a field into the scientific method. I want to move us closer to things like biology and chemistry or physics, these more reductionistic physical sciences. Reductionistic meaning we want to take a phenomena, whether that phenomena is an atom or a beam of light, or in Wundt's case, mental activity. We want to take a phenomena and we want to reduce it to its pieces and its parts so that we can understand it and understand how it works and what it does. We want to reduce its physical properties so that we can understand it. And so he set out to explicitly do that with the mind, with psychology. So Wundt and his colleagues and his students engaged in what's known as analytic introspection. He basically trained participants to describe their experiences and describe their thought processes in this sort of introspective nature, thinking about their thinking, in response to some variety of stimuli. So maybe Wundt would show them an image of a dog, and these participants would sort of let their mind go where their mind was going. Maybe it caused them to think of memories of a dog that they had. Maybe they're afraid of dogs, and so they have this fear response. And so Wundt trained them to sort of notice these thought processes and record them and sort of break down their maybe flow of consciousness into its structures, its basic elements. You might think of this, and maybe a good analogy is sort of meditation in a way, where you receive a stimulus and then you're just going to sort of introspect and meditate on what that stimulus is doing to you and your thoughts and your mind, and then recording what happens. Again, not how we do cognitive psychology today. This is problematic for quite a few reasons, but it is the very first attempt at doing something scientifically with psychology, and specifically cognitive psychology. Then in sort of the later 1800s, early 1900s, we get what I would consider, along with Donders actually, the first real studies of something that looks like modern day cognitive psychology. And this is Ebbinghaus, and he was studying memory and how difficult or easy it was to remember and then forget certain pieces of information. Ebbinghaus used nonsense syllables. I think he called them trigrams. They were basically just series of 3 letters that don't mean anything. So AQI, right, is a meaningless series of letters, or ZTL is a meaningless series of letters. And Ebbinghaus would randomly generate these nonsense syllables, as he called them, and have a whole list of them, and then try to study that list until he could remember it perfectly with no errors. And he would chart how long does it take him, right? How many times does he need to study a list in order to remember it perfectly? And then he would take a break. He would set the list down. He would go do something else, and then come back after an hour, maybe after 4 hours, maybe after 8 hours, maybe after a day, maybe after a week. And he would see, with that interval, how much could he still remember. And he measured how much he could still remember by the number of times he had to study the list again in order to remember it perfectly. So he gets the list down. He can remember the list perfectly. He takes a break, and then he comes back and he sees how many times does he have to study the list to remember it again. He found that after these short intervals, it took fewer repetitions of the list in order to learn it better. An interesting thing that he found is that the longer this interval, the worse his memory for the list, right? This makes intuitive sense now, but he's the first person to find this, that memory degrades over time. An interval of 1 hour, he's still pretty good at remembering the list. An interval of 4 hours, he's a little bit worse. An interval of 8 hours, he's even worse. An interval of a day, he's getting pretty bad at the list, right? Those memories that he created of these nonsense syllables are fading over time. So he called his sort of measurement of this was called savings. It's a little, maybe he could have come up with maybe a more intuitive way of calculating this or studying this, but this is what he did, and so we'll break it down and figure it out. He looked at first the original time it took him to learn the list the first time, minus the time it took him to relearn the list after some delay. So let's imagine that over here on the right, we have this figure. Let's say that it took him, at the first try, 1,000 seconds to learn the list. So it takes him 1,000 seconds to perfectly learn the list. Then he waits for an interval of 19 minutes, and then he tries to learn the list again. But this time, it only takes him 400 seconds. He's much faster at relearning the list after a delay of 19 minutes. So what he's saying here is that this original learning saved him 600 seconds. Right? It took him 1,000 seconds to learn the list the first time. 19 minutes later, it only takes him 400 seconds to learn the list. So an interval of 19 minutes has a savings of 600 seconds. Let's look at a different interval over here, B. He learns the list the first time, takes him 1,000 seconds. He waits a whole day. He comes back the next day, and this time it takes him 650 seconds to relearn the list, right? It takes him longer than the 19-minute delay. So something degraded, right? Memory was worse after 1 day than after 19 days because it now took him 650 seconds to relearn the list, meaning the original learning on an interval of 1 day only has a savings of 350 seconds. And if we go to 6 days of an interval, it takes us 730 seconds to relearn the list, meaning a savings of 270 seconds. So the big thing to notice here is that when we have short intervals, we get a lot of savings, right? We still have good memories of that original list. It saves us time. As our intervals increase from 19 minutes to a day, from a day to 6 days, as our intervals increase, our savings decreases, meaning we forget, right? It takes us longer to relearn the list. But one crucial thing that Ebbinghaus learned in all of this is that forgetting is not linear. I'll say that again. Forgetting is not linear. Forgetting occurs rapidly over the first 2 days. So we imagine this as this y-axis here is your percent savings. Just think about the y-axis as how good your memory is, right? That's just another way that you could think about this. After 19 minutes, memory is still really good, but memory drops a lot after only 1 hour. It continues to drop after 8, almost 9 hours, drops over a day interval, 2 days, but then after 2 days, memory kind of levels off. Notice that an interval of 6 days is not much different from an interval of 31 days. So forgetting is very rapid at the beginning with short delays, but then memory stabilizes long term. So even if Ebbinghaus came back a month later, he still remembers a little bit of that list. It's not completely gone, right? If this was linear forgetting, right, then we would sort of continue on this line and memory would be like 0 after a week. Right? But it's not. Memory doesn't fall to 0. Memory falls quickly and then maintains itself at a moderate level. A good analogy for this is language learning. So most of us probably had to take a language in high school and or college. I took Spanish. I actually took, I took Spanish in 8th grade and then every year in high school. So that's 5 years and then 2 years in college. So I ended up taking Spanish for a total of 7 years. I've been to Peru. I've been to Mexico a few times. And I was probably, I don't want to say I was fluent, but I was nearing fluency. I was conversational in Spanish. I could speak to people in Spanish and communicate perfectly well. I listened to Spanish radio. But I couldn't do that today if you asked me to, right? It's been a decade since I've done those things. But I still remember some of that Spanish. I could still get by, right? I still have some of that memory. So when I stopped using Spanish, my abilities in Spanish, my memory for Spanish vocabulary, grammar, and usage, my memory for Spanish declines rapidly, and then it stays steady for the next, decade, 10 years. And in fact, there is a decent amount of research on remembering language learning. And we find that if you really commit to learning a language and then you stop, you'll maintain about 33%, about a third of what you learned for the rest of your life. because memory declines rapidly and then stabilizes over time. Okay. The founder of American psychology was William James. He did not do experiments. He was really more of a philosopher who was starting to do psychology, and that he was thinking about consciousness, attention, memory, perception, imagination, reasoning. But the real advancement that James made in the study of psychology with his publication of the famous book Principles of Psychology, it's 2 volumes, was he began asking why questions. Why does the mind function that way? Why does consciousness do what it does? Why does memory do what it does? Structuralism, so Wilhelm Wundt, you could even say Ebbinghaus, as well as Donders, were asking what and how questions. Very just sort of, they're reductionistic, right? What is memory? How does it degrade? What is the decision? How long does a decision make? James began asking why questions. However, at some point in the early 1900s, these methods and this perspective on psychology was called into question, particularly by a psychologist named John Broadus Watson. I actually share my undergraduate alma mater with John Watson. He went to Furman University, as did I, in Greenville, South Carolina. And my early training as an undergrad was actually done in the John B. Watson Experimental Psychology Lab at Furman. However, Watson was not kind to cognitive psychology. Ironically, I did cognitive psychology experiments in the laboratory named after him. He would not have been very happy with that because he touted what's known now as behaviorism. So he basically looked at Wundt and James and all these people who were just kind of introspecting about the mind and cognitive psychology. And he basically said, this is bullshit. Because you don't have any clear methods. You don't have any experimental control. Everyone's inner workings of their mind could be different and vary. It's difficult to verify these accounts, right? People could just be making shit up. So Watson said, enough with this nonsense. We need to just look at behavior. Because remember, as we said earlier, one of the problems with cognitive psychology, especially back in the 1800s and early 1900s, is we can't measure the mind directly. We can't see the mind. We measure behavior, and then we make inferences about the mind. And Watson said, that's not appropriate. All you can study is behavior because that's the only thing that we can see and observe. And we need to be even more like physics and biology and chemistry. They don't make inferences or assumptions. They simply study what they can see and what they can measure. So Watson founded behaviorism. He wanted to eliminate the mind as a topic of study and only study observable, repeatable, quantifiable, direct behaviors. So Watson gets credit for doing something that's a very good idea. He wants to make psychology more grounded and even more grounded in the scientific method in the physical world. That's great. And we are that today, and we owe Watson a debt of gratitude for making that push. But as with most maybe radical shifts in viewpoint, he probably went a bit too far, because what he ended up doing and saying is that the mind doesn't matter. And we know now that that's wrong. Now, Watson was living in a time when we didn't have access to the mind, so maybe we give him a little bit of the benefit of the doubt. But the viewpoint on a whole is problematic. Behaviorism taught us a lot, and behaviorism is right about a lot of things, particularly learning. But but behaviorism was wrong to eschew the mind. And so cognitive psychology had to sort of battle its way back from behaviorism. And so that's what we're going to see here. Watson essentially called out the sort of analytic introspection movement with this quote: psychology as the behaviorist views it as a purely objective experimental branch of natural science. That's great. I want that too. I would agree that that's an important statement. Its theoretical goal is the prediction and control of behavior. Wouldn't necessarily agree with that statement. Introspection forms no essential part of its methods, nor is the scientific value of its data dependent upon the readiness with which they lend themselves to interpretation in terms of consciousness. Basically, Watson stood up and said, you guys don't know what the hell you're doing. This is all nonsense. Let me take over, and I'll make psychology a real science. So behaviorism, we're not going to spend too much time on it here, but we need to spend a little bit of time on it so that we can understand how cognitive psychology came back. Behaviorism said theories should be simple. They should be parsimonious. And objectivity is the holy grail of science, right? It being purely objective, a pure objective observer of the world. And introspection is not objective. So we should only measure behavior. And he agreed, and he leaned on philosophy as well. Some for you interested in philosophy, Immanuel Kant, who claimed, and Watson agreed, that mental processing could not be and never will be measured. They ended up being wrong, but that's okay. You can't get everything right. We can describe behaviorism as SR psychology, stimulus response psychology. Watson is interested in presenting a stimulus to a participant and then recording their response. That's it. A stimulus leads to a response. And then we can vary the stimulus and we can see how the response varies. Easy, right? Very objective, very clear, quantifiable, and measurable. That's all that Watson cared about. He called the mind a black box. Presumably things happen in there. I don't think he ever denied that the mind did things. Right? The mind obviously is doing something. Watson just said it's a black box. We have no lights to turn on inside that box. We have nothing. We have no flashlights. We can't see anything in the box. So if we're going to be serious about being a science, then we shouldn't be trying to measure the box. Just ignore the box. The box is there. Some things happen in the box, and then we measure the response. But we're not going to try and make assumptions about the box. So Watson, again, applies a stimulus to an individual and then measures that individual's response, but he doesn't care about your face. Right? He doesn't care about your mind. It's a black box. All that Watson cares about is how does the stimulus and then changes in the stimulus produce a response and then changes in responding. He had a series of famous experiments. The most famous, or now infamous, one is little Albert. I'm sure you've all seen this before, so we'll just kind of quickly go over it. Watson basically decided to scare the shit out of a 9-month-old infant in order to learn about fear responses. So Watson would take a hammer and a metal bar, and he would present little Albert with a rat, a white lab rat. And the baby has no reason to fear the white lab rat, right? It's kind of cute and fuzzy, and it walks around, and he pets it. And then Watson comes up behind Albert and clangs the hammer and the metal bar together, producing this very loud, very abrupt, out of nowhere noise that obviously scares a 9-month-old. So Watson gives him the rat, scares the shit out of him. Gives him the rat, scares the shit out of him. Eventually, not surprisingly, little Albert comes to fear the rat, right? He has learned to fear the rat. Stimulus response. And then Watson and his graduate student, Laura Lee Rayner, would go on to do things like present little Albert. These are actual pictures of them. Present little Albert with a bunny and see if, okay, he's scared. We taught him to be scared of a rat. Does that generalize to being scared of other fuzzy small mammals? And in fact, it did. We can see little Albert fears the rabbit as well as the rat. He has generalized his fear. And in fact, little Albert would go on to be afraid of a whole host of white fuzzy things, including men with white Santa Claus beards. So basically, Watson and Rayner created this little boy that would go on to live a life not knowing why he had this crazy fear of white fuzzy things. We never really found out who little Albert was. At the time, Watson and Rayner were at Carnegie Mellon. No, Johns Hopkins, I believe. And I think they think little Albert was the son of one of the nurses at the hospital at Johns Hopkins. But we lost track of him over time and with history. Okay, so this is called classical conditioning. Pairing a neutral event with a stimulus that produces an outcome. And it was inspired by something that we've all heard of, Pavlov's dogs, right? We'll do this really quickly because we all know what Pavlov's dogs is. Dogs have a natural response to food, which is to salivate. We then pair that stimulus that produces the natural response with a neutral stimulus, a bell. Pavlov actually used a tuning fork in the original studies. So we pair food with the neutral stimulus, the bell, and eventually the bell comes to elicit the salivation. So food makes dogs salivate. Bell doesn't do anything to the dog. But then if we pair the bell and the food, bell and the food, bell and the food, bell and the food over and over and over again, eventually the bell comes to take on the properties of the food and elicits salivation by itself. Funnily enough, a little sidetrack story time. Pavlov was not a psychologist. Pavlov was actually a chemist and medical doctor, I believe a medical doctor, studying gastrointestinal chemistry. He was for the Russian government. He was studying how our gastrointestinal system breaks down food. So he needed to study saliva. So he had a lab of dogs, and he would give them food, and he would collect their saliva in these little vials that were attached to their salivary ducts, and then they would, study the chemical makeup of that saliva. But what he noticed, and the reason that he started doing these experiments that we would now call psychology, was that he noticed that the dogs started salivating just when he walked in the room, even before he had given them the food, which meant that the dogs had learned to associate his coming into the room with the presentation of the food, just like Pavlov would go on to teach them that the bell can be associated with the food and then elicit the salivation. There's actually a great fountain. I've never been to it, but one of my professors in undergrad did. A great fountain in, I think, St. Petersburg. I might have that city wrong. One of the major cities in Russia. And it's Pavlov surrounded by dogs, and it's a fountain, so it's got water all around it. And it has a bell system, and the bell will chime, and then water will shoot out of the dogs' mouths as if they're salivating. So if you ever get a chance to go to Russia, take a little sidetrack and visit the Pavlov fountain. Okay, someone you've all probably also heard of, B.F. Skinner. He came along and built upon what Watson had done with classical conditioning in behaviorism, and he added what's known as operant conditioning, which is like a system of reward and punishments. So Watson is just classical conditioning, which are associations. Skinner is rewards and punishment. And of course, he found that if you reward a behavior, that behavior is likely to be repeated, right? Stimulus, response. If the stimulus is a reward, then the response becomes more likely. If the stimulus is punishment, then the response is less likely to be repeated. This approach dominated psychology through much of the mid and early 20th century. and really to the detriment of cognitive psychology. So again, operant conditioning. A behaviorist would explain, like, why do you go back to your horrible job with your terrible boss? If you've never seen the movie Office Space, please pause this lecture and go watch Office Space. Why do you go back to your job that you hate? Well, an operant conditioning behavioral psychologist would say that you're rewarded for it, right? There's a positive consequence. You get paid, right? They give you a paycheck at the end of every week or 2 weeks. And so you continue to go back. You do more of that behavior until the point when the negative consequences become too great, right? And then you will begin to do less of that behavior. Maybe your boss becomes so negative that you quit. Right? So some other examples of operant conditioning are like gold stars on your homework. That's what we call positive reinforcement. Spanking, which is a form of punishment. And timeout, and then letting you out of timeout, which is a negative reinforcement. We're not going to go into these details here. They're not super relevant for this class. Just know that your life is full of these operant conditioning, what we call operants, and they work. Just because we can say behaviorism made some mistakes doesn't mean it was wrong about everything. These operant conditioning and classical conditioning paradigms are a substantial part of your life and do impact your very real responses and behaviors every day. So, starting in 1868, we saw sort of the very beginnings of something we might call cognitive psychology. We saw that sort of gaining traction and gaining ground and sort of fusing with philosophy. And then we get this schism, right, in the late 1800s, early 1900s, where behaviorism starts to slowly take over into the early and mid 20th century. Now, again, behaviorism was good in the sense that we learned a lot about the way stimuli affect behavior and responses, and they went a long way towards formalizing psychology as a scientific and objective and reductionistic science. But the pendulum probably swung too far in their ignoring of the mind. We have a few very prominent cognitive psychologists to thank for never really letting go of the mantle of cognitive psychology, particularly Tolman. Tolman thought you behaviorists have it all wrong, and I'm going to use experiments to show you that you have it wrong, which is the best way to do science, to do science in order to spite other people. But in doing so, Tolman actually taught us a lot and is considered one of the fathers of modern cognitive psychology, leading to what today we call the cognitive revolution. So Tolman trained rats to find food in a maze. And what he found is that no matter where he put the rat, it went to the specific arm where it had previously found food. So I want you to think about a maze that's basically a plus sign, right? We have a vertical piece of the maze, and we have a horizontal piece of the maze. So you have sort of 4 arms, right? That's what we'll call each line on our plus sign. And at the end of each arm is like a goal box. It's a place where food can be put. So he puts the rat in one of the arms, and the rat learns the food is right in front of me. Boom, I just run straight to the other end, and I eat the food. I run straight to the other end, I eat the food. I run straight to the other end, I eat the food. Then Tolman takes the rat and moves it to the right. So imagine the rat was starting at the bottom of our plus sign and running straight up the vertical line to get the food. Tolman then moves the rat to the right, so now it's on the right-hand side of the horizontal line of the plus sign. And now to get the food, the rat has to come to the center, and the rat has to remember, the food is no longer straight because I'm in a different place now. I need to turn right? I need to go to the middle and then turn right to go up to get the food. And what Tolman found is that the rats figure this out really, really quickly. And so what the assumption he made, again, the problem with cognitive psychology, we have to make some inferences and assumptions, is that the rats create a cognitive map, a representation of the maze in their minds that they can manipulate based on where they start in the maze and use that cognitive map, that representation, to find the food quickly. So if you put the rat on the left-hand side, it would know to go straight to the middle and turn left. If you put it on the right-hand side, it would know to go straight to the middle and turn right to get the food. And so what Tolman said is, this has to mean that the mind is good for something, right? The mind is not just a black box. Something really important is happening in here. They are representing space, right? Physical space of the maze in their mind and using it, deploying it in a functional way. So, I'm sorry, I forgot I had this slide. Would have been much easier for me to explain this visually with this slide, right? So, the rat learns that no matter where it's put in the maze, right, it learns how to get to the food, even though here it's got to turn left, right, and here it's got to turn right. And again, another experiment by Tolman in 1948 that confirmed the use of these mental maps by rats. I know I have an image on this one, so let me flip to it and I'll explain. Ooh, sorry, that's a little fuzzy. Basically, Tolman started rats here at the bottom, and they learned to run straight and get the food. And he would also put them in this maze with no food, such that they could just explore the maze, right? Notice how there are 3 paths to the goal box, to the food. You can run straight in a direct path A. You can take this little detour called path B that gets you to the food. Or you can take this long detour called path C that gets you to the food. Now, if the maze is just completely open, then just go straight, right? Obviously, take path A. It's the fastest way. Get the food. You're hungry. So Tolman let the rats explore this maze, and then he put up barriers. So one place where he would put up a barrier is right here at place X, and another place he would put up a barrier is right here, place Y. Notice that if the barrier is at place X, then you can't go straight, but what you should do to be most efficient is to take path B, right? That gets you around the barrier, and boom, you can go straight to the food. Path C will get you to the food, but you're taking too long of a detour, right? It's inefficient. Notice that if the food is if the barrier is at place Y, then path B does nothing for you because you still run into the barrier. If the barrier is at place Y, you need to take path C. Well, Tolman found that the rats could do this perfectly fine. If the barrier was at place X, they knew to take path B. If the barrier was at place Y, they knew to take path C, thus confirming the existence of some representational mental map of the maze in the rat's brain. Another set of experiments that presented some problems for behaviorism were McNamara, Long, and Wyke, or Wiki, I'm not sure how to pronounce that, 1956. They basically took some rats, let's imagine this is our rat, and they put it in a little cart, and they pushed it around the maze. And the rat still creates a mental map of the maze, and regardless of whether the rat ran the maze or the rat was carried around the maze, their performance was about equal on correct responding to find the food, right? So whether they were carried in this little cart, they performed relatively well and equivalently to had they actually run the maze themselves. This is a problem with behaviorism because behaviorism theoretically requires a response for there to be learning, right? Stimulus, response. If the rats are carried around the maze, then they're not responding. They're incapable of responding, right? Their movements are not controlled by themselves. They're controlled by whoever's controlling the cart. That's a problem for behaviorism because it means that responses aren't necessary for learning because something is going on in the mind. The mind is doing the learning. That even though you're carried in a cart, you can still observe the world around you and learn and create this mental map and then deploy that mental map as needed. So these studies start to come out and people start to realize maybe behaviorism wasn't all it's cracked up to be. Maybe we really do need to start studying the mind. And one of the big declines of behaviorism, one of the big missteps that Skinner made, was in his arguments over how children acquire language. Skinner argued that children acquire language through operant conditioning, reward and punishment. Children imitate the speech that they hear, and then they're rewarded when they produce it correctly, right? We clap, we smile, we praise them. If they ask for a cookie, we give them a cookie, right? That's a reward, right? The child created a situation where they could be rewarded for their actions. And so Skinner is basically saying this is how children learn language, through this system of rewards and punishment, operant conditioning. Unfortunately, Skinner ran into the person who was probably the most influential academic, other than like Darwin and Einstein, in the entire world, and that was Noam Chomsky. Noam Chomsky originally began studying language acquisition in children. He went on to publish in many, many fields: politics, philosophy, ethics, as well as many fields in psychology. One of the most widely published and cited thinkers and scientists of all time. He basically showed that children do not learn language solely through imitation and reinforcement and conditioning, because children come up with things that they've never heard, right? They produce sentences and ideas that no one has ever said to them before. So they can't be simply imitating and then receiving reward. And children say things that are incorrect and that they have not been rewarded for. These are called preservative errors, and they're actually a sign that a child is learning language correctly. So English is a good example because English has lots of irregularities. So the word run is in the present tense. Its past tense is ran, right? That's an irregularity, because how do you typically make a word past tense? You add ed, right? So if I drop a bowl of cereal, drop is in the present, but drop the ed is in the past, right? That's the normal way we make something in the past tense. We add an ed. And so children will say funny things like I runned instead of I ran, right? I runned. It's technically a mistake because the word, the conjugation of run to ran is an irregularity. It should be ran. Ran is correct. Runned is incorrect. But the use of ed, the overuse, the preservation of ed, is actually a sign that the child is learning language. And even though it's incorrect, they're not rewarded for it. They will continue to say it because they're applying this sort of biological program, Noam Chomsky argued, this inborn biological program for learning language and picking up on the patterns of language. ED being a pattern of language in the English language. So Noam Chomsky basically wiped the floor with Skinner when it comes to language learning. Skinner just happened to get into an argument with a guy that was a very poor idea to get into an argument with. And Chomsky basically showed that Skinner was completely wrong about language learning. Okay, so let's stop there. That's sort of our halfway point in chapter 1. We've discussed the history of cognitive psychology, as well as what cognitive psychology is. All of this stuff leads up to basically what we're going to call the cognitive revolution, which is this explosion of cognitive psychology research that happened in the 50s and the 60s when everyone realized maybe behaviorism wasn't the best way to do psychology. And so we're going to pick up on part 2 of this lecture and talk about some major themes in how we study the mind in modern cognitive psychology. So thanks everybody for listening. The static PowerPoints will always be in iCollege for you to look up if you need to. And you can play this video back as many times as necessary, as well as part 2. So thanks for listening, and we'll pick up at this point with part 2.